All right, welcome back to another one. My name is Jesse. I am a tutor in Melbourne and I make GAMSAT videos for section 3. Today what we're going to do, diving right in, we're going to do the fourth of the physics crash course, looking at wave theory and also optics and light as well. It should be a little bit of a shorter one than some of the usual ones. As I always mention at the start, the kind of content that's in this, it is very much content based. Yes, GAMSAT is reasoning based. This is designed for people with a non-science background or people who have not done physics before or haven't done physics in a while and need a bit of a refresh on it. It is going to get people up to speed with the basic fundamentals of physics and each topic that you need to reason through the GAMSAT. No, they're not going to ask you to just straight up use formulas and assess it like a uni subject would or a high school subject would. We only need to know it to year 12 physics levels of reasoning. But the idea behind this video is just to make sure that people have a working understanding of the principles behind it, which then makes it a lot easier to actually break down the information. If you were to go in just on reasoning, I hear a lot of people talking about, oh, it's just a reasoning exam, I'll just go in and just rely on the information given. You're setting yourself up for failure there, because while they're not going to assess content directly, familiarity with the content is going to be the key to being able to answer every question. You've got 75 questions in 150 minutes. The time moves very, very fast. 2 minutes a question might seem reasonable, but you've got to factor in reading, comprehension, and then tackling it as well, and also ruling out options. So we have to have kind of hit the ground running when we actually read the questions and the stems to know exactly what to do, and that's what this series is really for. So the first thing that we'll do here is we'll go through wave theory. There's not really a lot that we need to go through. It's just familiarity with the two forms of waves and kind of their features as well. So the first thing is you can see we've got two types. So we've got longitudinal waves, and then we've also got transverse waves as well. So longitudinal waves, you won't really see these all that often, but just in case they come up, we're thinking of particles basically oscillating backwards and forwards and bounding into each or bumping into each other, knocking the next one, and this is how we can transfer energy. Everything with waves is about the transfer of energy across a medium of some sort. And so what we have here are all these lines representing, you could think of them as particles or wave fronts, and when they get closer together we call these compressions, and when they get further away we call them refractions. And the idea is that the particles would be compressing in one spot and then bouncing off and then spreading out, recompressing. And so the idea is that the particles are oscillating backwards and forwards, and that energy transfer should be in one particular direction, like that. The key thing from this is both the particles and the energy move in the same plane, whereas if we were to look at transverse waves, it's going to be a little bit different. So before we move on, longitudinal waves, the only time you'll ever really see them being talked about is in the case of sound, even though sound can be represented as a transverse wave as well. In terms of longitudinal, we can think of the air particles as kind of bumping into each other, and this is then how the energy is going to propagate through the air or through the medium or whatever that actually is. So a simple way to think about it is, or a simple example that you might be familiar with, is if you think about the old Western films and everything, when the bandits or whoever it was, cowboys, blah, blah, were putting their ears on the train tracks to try and hear if a train was coming. So that's actually using the concept of longitudinal waves. When you've got particles moving in a gas or in air, they're obviously able to move at a certain rate, but it takes a little bit longer for them to move through it because they're more spaced out. Whereas if you've got particles bumping into each other in a solid, like a solid steel railroad track, then the particles are much more close together. They're in a rigid structure, which means they're going to bump into each other much faster, and you're able to propagate energy more quickly, which means the sound travels down the track a little bit faster, and you can hear a train coming and have a little bit more kind of time to work out what you're going to do. I don't know, I don't really watch Westerns. Then the transverse waves, so these ones are where you've got the particles still oscillating, but this time they're going to be oscillating up and down. Can't draw a straight line. Like this, but the energy will still be going in this direction. So now we've got particles propagating at right angles to energy propagation. That's kind of the key feature if we were to take any summary from it. In terms of describing them and their aspects, or quantifying them, we've got the amplitude, which is just the vertical deviation from the midpoint, or the kind of average central position of the particles, and they can oscillate upwards and downwards. So we only look at amplitude as being just the absolute deviation. So you can measure the amplitude down this way, but it won't be negative, it'll just be an absolute number. then the width of one cycle of the wave before it repeats itself, so we can see that here we've got a repeating section between each of these orange lines. And so what that means is the width or the length of that section is going to be a wavelength, so the length of one wave. We usually use lambda to represent this, and it's also related somewhat to frequencies and velocities as well. So frequency is the number of wavelengths that pass through one point in 1 second, measured in hertz. So in order to understand that, we need to know how long it takes for one wave to pass through, and that is what this T here represents. So this is the period of the wave, which is, rather than being the wavelength, it's the time that it takes for that wavelength to pass through, right? And that's going to be dependent on the velocity. So the frequency is the inverse of the period. So if every wavelength takes, say, 0.1 seconds, then that would mean that the frequency is going to be 1 over 0.1, which is going to be 10. Measure that in hertz. And remember, hertz means wavelengths per second, like that. So it's really a measure of distance per second. So it's a kind of like a velocity. And so if we think about that, we're really dividing 1 second by the fraction of a second that one wavelength takes. So if one wavelength takes 1/10 of a second, well, then that means we can fit 10 wavelengths into 1 second, right? And that's where the 10 hertz is coming from. Cool. And then finally, we have velocity is equal to frequency times lambda, or wavelength. So if you think about it again, frequency is measured 1 per time times the wavelength. If we put the units in, 1 per second times by, and this is meters, so then if we times those together, we get meters per second, which is the measurement of velocity. So that's how I always kind of remember rules. They'll really give you rules, to be honest. I don't think they would necessarily expect you to know this formula. They would probably give you that in the STEM. So, but if ever you need to reason it out, always look to the units every single time. And so I won't really bother with the subbing in. Like, obviously, simpler physics questions in the GAMSAT, that you can have them, is just going to be getting you to basically plug in numbers and then solve the missing variable. I think we all know how to do that, or at least I've covered all that kind of stuff in the maths videos and everything. So that's really all we want to look at there, is the key features between them, how we measure them, and how we describe them as well. So then next up, I'll zoom in a little bit here. So now we're just going to look a little bit more at light specifically, right? So light, it is jumping a little bit. We're not really looking at it as a wave so much, because physics in GAMSAT is not really that concerned with the wave-particle duality of light. So, I mean, if anyone's interested, I can turn that into another video, or you can check out, I'll probably end up doing a VCE video for my VCE students. But in terms of light, what we want to think of first of all is, what is it made of? So photons are going to be what we'll call a light particle. It's not really a particle because it doesn't actually have mass or anything, so that's what m equals 0 means here. We can think of it as a packet of light energy, right? So we're trying to quantify it and, you know, kind of reduce it down to say that it's a particle, kind of like an electron, but it's not actually something with mass, right? It's just a way of theoretically understanding it. Really, it actually has a lot of wave properties, and that's where the wave-particle duality thing comes in. So then the next thing is velocity of light. So we take the velocity of light as a constant. It is c, right? Represented as c, the speed of light, 3 × 10⁸ meters per second, 300 million meters per second. And the other thing is, we can assume that light will move in straight lines. If we were to get into deeper physics, which is not covered in GAMSAT, yes, light can bend under particular gravitational strengths and that kind of thing, but we're just looking at light moving in a straight line, so we can assume that when it bumps into something, it'll bounce off in a straight line and so on. There's no curvature to it or anything like that, so it simplifies the questions. And so then we can look at the behavior of light when it's interacting with different surfaces and materials. So the first one is reflection. So this one, kind of self-explanatory. If you've got light reflecting off of a surface, I think we're all familiar with that. What we want to think about more so are the angles that are made with that surface, right? So if you've got a light ray here, this is going to be our photon, just here. And if it's traveling in a line at an angle to the surface, we generally measure the angle against the normal, which is this vertical line here, so the line that is at a right angle to the surface itself. We measure the angle out from the normal to the ray of the light's path, and then we call this here the angle of incidence, right? So this is the incident ray, so the one that's incoming, and then we have the angle of reflection, because this is the reflected ray. And the idea is that the angle against the normal of the incidence should be exactly the same as the angle of reflection, like that. Using a bit of like trigonometry as well, we can also assume that, or geometry, we can assume that this angle here, probably shouldn't use theta, let's use alpha, should be the exact same as the angle against the surface as well, like that. But mathematically, we use rules that relate areas or relate angles to the normal. That's all we need. Really simple example is just think about like throwing a tennis ball at a wall, right? It should, ignoring energy loss and all the rest of it, it should bounce off and reflect off the wall in the same way that light would on that path, right? The angle should be the same. So then next one, very, very similar word, refraction, slightly different though. So this is not something reflecting off the material and back into the original medium. It's now passing through into a new medium. So this could be light going from the air into the water. It could be light coming from water up through to the air. It could be going through two different gases of different, what we call optical densities, which is going to be N. It could be anything at all where you can transmit light through it. Generally speaking, it should have a different optical density, and so therefore it's going to bend or change the path of the light slightly based on that optical density. So optical densities are just constants for different materials. They would give you those in the question if you need them, or else you would mathematically solve them with given information. And all we want to understand here again is the angle of incidence, same idea. It's the angle against the normal, so that's what the N means. And we've got this border here. Below is going to be medium 2, above we're going to call medium 1. Medium 1 has an optical density of N1. Medium 2 has an optical density, we're going to say, of N2. These are usually numbers like 1.0, 2.5, 0.8, that kind of thing. And we can always assume that air has an optical density of 1.0, like that. So everything's in reference to air. And so the light, you can see, bends. Instead of following the path that it would have followed if there was to be no interference, it's going to bend it in because of the change in optical density. And then you're going to get a smaller angle here against the normal called the angle of refraction. So the angle of incidence and then the angle of refraction. And then we can mathematically relate them. So the relationship is that if N2 is greater than N1, so that is you're heading from a less optically dense to a more optically dense material, then that will mean that the angle of refraction will be less than the angle of incidence. You can see because of that bending inwards like this. So if this was air and this was water, then this is exactly what would happen because air has an N of 1.0. Water, I actually don't know exactly. I'm just going to say it's maybe 1.3, I think, from memory. And so then that ratio of them is going to affect the angle. And this is exactly why if you put like a straw or a spoon in a glass of water and it kind of has that look where it's, draw it out like this, you got the water, you got the straw, and it kind of looks like it's doing this. And that is because of refraction of the light overall. All right, get that out of the way. And same thing, so if you're going from a more optically dense to a less optically dense one, i.e. N1 is less than N2, it'll go the other way. So that would then actually allow the light to bend less and go out this way instead, and your angle of refraction would be much larger than the angle of incidence, like that. Cool. So again, we're not really diving into calculation quite as much because it's just about understanding the relationships between these things. A lot of the questions will actually be about ranking things and that kind of stuff. So understanding what makes things less or more is actually often what you really need. The ability to manipulate formulas is a math skill, not a physics skill. So we're focusing more on the principles themselves today. Then we have over here Snell's law. So this is really the mathematical relationship between them, which I'll briefly mention. So you can actually relate the angles of incidence and refraction using the sine ratio, and then also with the optical densities. So the first medium's optical density times by the sine of the angle of incidence should be the same as the second optical density times by the sine of the refraction, like that. And so in that, if you were given Snell's law, you wouldn't have to know Snell's law, I don't think. I think, again, that's something that they'd reasonably give you. They don't seem to be really expecting anyone to know any complex formulas anymore. The only ones that I've seen them kind of rely or force people to rely on are things like Ohm's law or some of the basic stoichiometry, like in chemistry, like number of moles is mass over molar mass and that kind of thing. Otherwise, though, anything more complex than that, they're pretty much giving it to you and usually defining all the variables and everything else. But understanding all of this means that you can just kind of skip over that. You don't have to read the preamble, and you've also got a working understanding of it, because sometimes they don't give you a full explanation of how to use it. They just define the variables, and they actually are expecting people to bring their own previous knowledge into the question. So this here can prove that. Now, obviously, in this rule, if you were to be using it, manipulating it, you have to be able to estimate sine of different angles. So you don't have to be super specific, but a tip for how to do that is, if you know that sine of 30 is half, that one, commit it to memory if you don't already know it, sine of 30 is half, right? And we know from basic trigonometry that sine of theta is opposite over hypotenuse, right? So the side that is opposite the angle, and then the hypotenuse of the right angle triangle formed. So even though there's no triangles here, you can use a triangle to theoretically understand the relative size of sine of an angle. So if we know this one in blue, sine of 30, we know that must be 1 to 2 as a ratio. Could be 2 to 4, 3 to 6, 2.5 to 5, anything, as long as the ratio is half. If we then were to increase the angle above 30 degrees, think about taking that hypotenuse of 2 and kind of just spinning it or rotating it to increase the angle, but keep the length the same. So what's going to happen then is this side is going to have to grow in the process, right? This is going to have to get bigger to try and meet that, right? And so this will have to be greater than 1. If we're keeping this constant, that then would mean sine of an angle greater than 30 should be more than 1 over 2, which means more than half. So now we know that sine of any angle greater than 30 should be greater than the value of half, and that should be enough to get you through, right? And then vice versa, you can go backwards, you can think about spinning that 2 down, reducing it, and then you'll find that this opposite now goes less than 1, so therefore sine of less than 30 is going to be less than half. And you can go all the way down until you get down to sine of 0, and that will be 0, so then you know any angle between 30 and 0 is going to have a sine value of between 0 and half. You can use a rough scale. It's not going to be a linear scale, so you've got to be careful with it, but like I said, it's multi-choice, so that should be enough to get you through. All right, moving along. So then the third behaviour of light is diffraction, and I think this one more likely they would give you a diagram or they would explain it to you in a little bit more detail. But diffraction is where we're treating light now not as a particle but as a wave, and we're looking at the constructive and destructive interference between the light waves, right? So what that actually means is if we take light now as following a transverse wave, and we put 2 light waves together, so I'm going to put the blue one, I'll put a yellow one. If I put the yellow one completely out of phase, so opposite like this, and I was to add them together, so they overlap, what's going to happen is the peaks and the troughs are going to cancel each other out, and you'll end up with 0. And here they're both at 0, so they add up to 0. Here they cancel out to 0, and you end up just with nothing. You end up with no light whatsoever if they have the exact same amplitudes, like this. So this is an example of destructive interference. It destroys the light and turns it into nothing. But you can also have light phases that are in phase, meaning that they actually overlap. So there's the blue one, and then let's do the yellow one, try to trace it. Obviously they're supposed to line up perfectly. So this time, both of their peaks are lining up, which means they'll add up individually. If these both have a height of 1, we'll say to quantify it, they'll add up to 2. And likewise, the troughs will go to an extreme, and then the peaks will go to an extreme, and you'll end up with constructive interference, where you actually get greater amplitude, so you get higher intensity light. Like this. And still at these points here, they're going to add up to nothing, right? So you get an increase, and that is constructive interference. So we can visualize if these yellow lines here are like light wavefronts, and they're traveling towards this pink border that has 2 little gaps or slits in it. What's then going to happen is those light waves are going to then bend, right, out into like curved wavefronts, kind of like if you drop a rock in a pond or something, and they spread out over time. I haven't drawn all of them in, but they will reach this white line, which has a screen on it. And so what's going to happen is, hopefully I've drawn this neatly enough, right in the dead center between the 2 slits, you can see that we have these little crosshairs here, here, and here between the wavefronts. And if we kind of trace a line, they should be in a straight vertical line, and I've not drawn it perfectly. But that should line up, and on the screen what we'll find is a bright band, right? So this is evidence of constructive interference, meaning that the peaks were all lining up. But there are other points where the troughs line up, the peaks and the troughs line up, and you get destructive interference. And so the way to find that is you can first trace out all of your constructive interference. So these are all the points where you have crosshairs. So I can see I've got a crosshair here, and I can actually go again, and I'm tracing here, and then it points me to another bright band, and then again, and then to another one. I've actually drawn that quite well. There we go. Did not expect that to happen. And then like that, and it would keep going out, right? If you look in between, I'll try to do this with a green line. You can see that now when I go right dead center between them, it's kind of zigzagging back and forwards across. It's not meeting crosshairs. So this is destructive interference, and so we get no light between them. So you get these bright bands and then dark bands. And this is what's called a diffraction pattern, which would be proof that light is behaving like a wave and not like a particle. If it was to behave like a particle, what we should see is just two bright bands directly opposite the slits, because the light should just be kind of filtering through almost, but it doesn't seem to do that. So again, that's a pretty heavy physics topic. It is in year 12 physics. I don't think they would necessarily, they wouldn't be testing your knowledge of this experiment and the data and everything. What they would probably do is present you with something similar, explain it, and then ask you to infer or kind of make some conclusions. And so familiarity with this is going to be pretty important, right, in that case, because it would massively help your reading and your comprehension of it as well. If you're interested in more about it, just Google the double slit experiment. You will find a lot of extra stuff, but you definitely don't need to know it for GAMSAT whatsoever. You just want to know that diffraction is a feature or a behavior of light when it's acting as a wave, and we just want to understand that it is when the peaks and the troughs line up, you get constructive interference, and then there are out of phase waves that cancel each other out and then give destructive, and you get a very specific pattern. That's it. Cool. And then over here, just a little bit more in terms of formulas. We're kind of jumping around because it's a bit of a disjointed topic. We can also calculate energies of photons. So the energy of a photon is given by h times c on lambda, which is also h times f. Now we've already seen lambda as wavelength, f as frequency in hertz, c was the speed of light, h is Planck's constant. And again, they would give you this in the question. They would definitely not expect you to memorize constants at all. There are two different ways to measure it. So there is 6.63 by 10 to the negative 34. That one is that's when you're working in joules. And then if you're working in electron volts, which is another measure of energy, for that one 4.14 by 10 to the negative 15. And that's when you're working in electron volts. Again, they would tell you which unit you're going to be working in. They would give you the constant. We're just going to mention them here now. So it's just a constant that plugs into the formulas relating to light. Cool. And now why is hc on lambda equal to hf? That would imply, looking at a bit of proportionality, c over lambda would be f. Then they must be equivalent. The h's can cancel. So if we think about that, c was 3 by 10 to the 8 meters per second over lambda, right, which is some number of meters like this. So we get 3 by 10 to the 8 over whatever lambda is, and the units, the meters cancel out, and then we get 3 by 10 to the 8 over lambda seconds, like that, right, or per second, I should say, per second. And per second is the equivalent of a hertz, like that. And that's the way that we can kind of reason that out. You can also think of it as its frequency is 1 on time, right? And then speed, c, is, speed, I'll just put s, and then lambda is a distance. So if you think about it, if speed equals distance over time, right, then time equals distance over speed. So therefore the inverse of time, which is hertz, 1 on t, is s over t. Like that. So there's all these little proofs in it. So I always use these to make sure that I was using my formulas correctly. You can mathematically prove any formula based on the units a lot of the time, or based on the kind of primary measuring tool, whether it's a mass, a time, or a length. Those are the three main dimensions of measurement. And then finally, just a bit of optics. They have this in the first ACER practice test. I have not seen it come up since. I remember getting it when I did the GAMSAT in like 2012 and 2013, but it's definitely changed a little bit now. I have not seen it since. It's not in test 2 and 3 from memory. and I didn't see it in March at all as well. I don't know if anyone's really talked much about it, so I'm not going to spend a huge amount of time on it, but it's definitely worth knowing because it uses the thin lens formula, and that is something that does seem to pop up here and there in GAMSAT, and it could have just been the luck of the draw in terms of the questions that I avoided it. I never really liked optics all that much, but they're kind of fun to draw. So with optics, we just want to look at how lenses technically just refract light in order to move or produce an image that is either real or virtual, upright or inverted, and then either diminished or enlarged. That's all we need. So first of all, we've got to understand the two types of lenses. So you've got this kind of almond-shaped one, which is a convex lens, and this will cause convergence of light. So it'll bend it inwards towards the axis. So if we take this as just the central position, the principal axis here, and we've got some light coming in at this position, the lens will bend it inwards onto its focal length. So it'll have a particular focal length which will determine how much it bends the light, and then this will help converge the light and form an image. Concave lenses, kind of like this, looks a little bit like an hourglass kind of thing. These ones cause divergence of light and actually bend the light outwards, right? Easy way to remember it, obviously they both start with C and this one's got C shapes in it. I just looked at this and I kind of went, it's kind of like a cave, like it's hanging over. This one, just remembered it as the other one. So we have to understand then how to do ray tracings with these different lenses. They operate in slightly different ways. But before we do that, we have to understand the notation. So we've got the object, which is the actual thing that you're forming an image of using the lens, and its position is given by lowercase u. V is going to be the position of the image that is formed, and then F is going to be the focal length that we saw before. The thin lens formula is here, and they usually, from what I've seen, give you the thin lens formula. 1 on the focal length is equal to 1 on the image position plus 1 on the, 1 on the object position plus 1 on the image position. You can do this in centimeters, you can do it in millimeters, you can do it in meters. You don't have to use standard units as long as everything is in the exact same unit. So if we were to do one here, and I might redraw this as well, if we have an object here, say it's a person standing here, we've got this gigantic convex lens, what we do is draw one line that goes straight across at that height and then bends through the focal length, and you just kind of extend it as far as you can. Then you do another line straight through the center, right, through the origin of the axes, and extend it all the way through, and they should meet at some point. And then finally, to confirm the image position, you run another one straight through the focal length on this side of the lens until it hits the axis of the lens, and then bend it straight across. So it's almost like an opposite of the first one. And then they should all meet at one point if it's drawn accurately enough. And then that will be the position of the image, and you can see it's underneath the axis. So what that means is the image is inverted, it's upside down. You can see it's taller. If I've done that roughly to scale, it's gotten larger based on the size of the focal length, so therefore it's magnified. And we call it real when it is on the opposite side of the lens to the object. If it's on the same side, like it's reflected back, then it's a virtual image. Those are the words that we need to use. As long as you understand how to use them, you'll be fine. So if we were to move the focal length, let's say we had a lens with a larger focal length, what that would do is move F out to here, and it would also bend it all the way back to here, which is going to cause all kinds of trouble. So then we do one that goes here, and then it actually bends through the focal length. Then we'd have another one like this, and you can see it's already going to go off the screen, like I can't even fit it on there. So you can imagine that it's still going to be a real image, but the problem is that it's going to be miles away. You can also do this one, but I've probably made that more complicated than it needs to be. You'd have to go through a whole thing. I'm not going to do that. They should all line up somewhere down here. It would still be real. It would still be inverted, but it would be massively more magnified. You can see it's dropping a long way away from the axes, so it'll be a much larger image. Then under here, this is how we work with concave lenses. So if you have an image, an object sitting in this position here at U, and again a focal length given, we're going to work out where the image sits this time. So with these, a little bit more complicated. So we still have in blue that line that goes right through the origin. You'll always have that. Then you have the same thing, you have a line that goes straight across, but because the focal length is here, it doesn't actually converge light, these ones. It diverges it out this way, like this. So it's not going to hit that focal length. So what's going to happen instead is we need to backtrace it this way to the focal length on this side. And you'll see that it meets up with the blue axis, or the blue line here. There's this tiny, tiny little arrow, which I might zoom right in. There we go. And then we also do another one that runs towards the other focal length. If you remember last time with convex, we did this, and like that. But the problem is that's converging the light. We want to diverge it, so we're going to go straight through like this, and then it's going to diverge straight like that. And if we backtrace that, it should line up with this position here as well. So what that means is this is our image, and you can see now the image is reduced or diminished. Might put diminished. It's upright this time because it's facing upwards. It's on the positive side of the axis. And then it's also going to be classified as virtual because it's on the same side of the lens as the object was. And that's it. So you can literally just repeat those steps, right? So if we turn those into actual kind of written steps, I don't know how well my handwriting will work with this, but if it's concave and convex, so step number one, let's just do the one right through. So we'll do trace from top of object through the origin, right? Because that will be exactly the same in both of them. The second thing that we did then was do trace horizontally, straight across, and then converge through F. Then step number three, so that was this one here. Then step number three is trace through F, and then converge to horizontal. It's often not even needed to do that third one, and then the point of intersection is going to be where the image is, just like that, right? And we can do the same kind of thing. So with concave, step number one, literally the exact same. Step number two, technically the exact same, but you'll have to backtrace because you have to diverge the light, right? Backtrace to F. And then step number three is run through the same thing through F on the other side though, and then run horizontal and backtrace like that. Backtrace horizontally, and then you get your image there. The point of intersection is the image again, and that's the two. Cool. So that's it. So that's how we do ray tracings, and this formula here is an algebraic way of solving any one of those three variables. If they're leaving one out, then from there you could do a ray tracing with all the information. Otherwise, that's everything there. So hopefully this has kind of cleared up some stuff. Like I said, I wanted to keep this one pretty short because optics is a pretty small topic. It's less likely than others from the physics stuff to come up. I think gravity and forces and kinetics and energy is much, much more likely. But even still, it's good to be up to date with everything. We want to have a really, really kind of comprehensive set of videos with these. So as always, hopefully this has helped, and I will see you guys in the next one.